Okay, great. Thank you, everyone, and thank you, the organizers. So, hello, everyone. My name is Zhuang. I'm a rising third-year graduate student at Keck, and I'm working with Evan Kirby, who is sitting next here. And I'm really honored to have this opportunity to share the work I've done with my collaborators, including Nisha Lito-Chavalet and other Australian collaborators listed here. So this talk will consist of two different projects that we've been working on, using both Keck and Palomar data to understand the stellar mass-stellar velocity relation for galaxies at different redshifts. So starting from the beginning, in 1979, the QATM measured the abundances of the heavy elements from the local H2 regions and find that there's actually a correlation between the stellar mass and the gas phase metallicities. So this is the mass metallicity relation, or MZL we call today. And later, a much larger sample study of local star-forming galaxies from small database also confirmed this trend by Tremonti et al. And the similar correlation was observed between the stellar mass and the stellar metallicity measured at the iron abundances. And several factors can play a role in shaping these observed MZR. For instance, the more massive galaxies usually have a deeper gravitational potential wells, so that they can retain more metals from either the stellar feedback or the galactic feedback that eject the metals away from the galaxies. Meanwhile, the active star formation can also enrich the gas of the interstellar medium. On the other hand, the inflow of those pristine gas and the outflow of the enriched gas can decrease the metallicity. So understand the shape of the MZR is actually very important because it can tell us a lot of information about how these evolving processes will change as the galaxy as the stellar mass grows. However, even though we have known this relation for a few decades right now, there are still many unknowns in its shapes. So the current observed MZR follow a single power law at the low mass range and flattens at high mass end. But the overall shape of these MZR across a full range of the galaxy mass is still unknown. So according to some previous studies on the gas phase MZRs, people have suggested that the transition may be very smooth. So like these green lines, the MZR just gradually flattens to the high mass end. However, Planck et al. Have argued that actually the transition will be very steep. So you can see there's a break in the gas phase MZR at around 10 to the 9.5 solar masses. And we also see the similar break in the stellar phase MZR, although the error bars are just too large to know whether the break is true or not. And if we only focus on the massive galaxies, there might be a redshift evolution. So for galaxies at higher redshift, they tend to be more metal poor at a given stellar mass. And the rest of the talk, I will discuss how we make use of the Keck and Palomar data to study these problems in the stellar phase MZR. So in the right plot shows the current observed stellar MZR at local universe. And you can see at around 10 to the 9 solar masses, there's a discontinuity between the high mass MZR shown by the green lines and the low mass MZR shown by the blue lines. And if both of them are correct, it is very likely that a break should be present in the stellar MZR at local universe. But this discontinuity may be an artificial effect instead. But if it is real, it is definitely suggests that we have a break. So the systematic effects comes from how we measure these metallicities. So for the dwarf galaxies, they are very close to us, so that we can resolve them into individual stars and measure the metallicity directly from the stars. But for more massive galaxies, they are much more further away. So we have to obtain the metallicity from the integrated spectrum. And if there's any systematic effects between these two techniques, it is possible that the high mass MZRs may go down a little bit, and then the transition would be smooth rather than a break. And in order to understand these questions, we observe NGC147, a dwarf elliptical galaxies in the local group on Palomar cosmic graph imager, so that we can obtain the integrated spectrum and measure the metallicity directly from the integrated spectrum. Meanwhile, we can also compare this integrated metallicity with the metallicity derived from the star. This comparison will allow us to put a new constraints on the systematic differences and also allow us to know whether the break is true or not. We choose NGC147 in particular because it is at a proper distance. It is close enough so that we can resolve some of the brightest stars on the Keck, but it is also far enough so that we can obtain the integrated spectrum for the central regions with just a few pointings on sky. And even though at the moment we only have one sample, it is actually very encouraging to see that the recovered integrated metallicity of NGC 147, which is shown by the red star in these two plots, actually falls on the low mass MZR shown by the blue lines. And it is not only for the traditional stellar MZR measured as the iron abundances, but it's also for the MZR measured as the magnesium over hydrogen ratio. And this consistency suggests that the break is actually should be present in the MZR local universe, because the systematic differences are just too small to explain the discrepancy between the low mass and high mass MZRs. And we get the consistent results. So it also let us know, now we can measure the correct metallicity from the integrated spectrum. So now we can also trust the MZRs for these high massive galaxies. Now let's take a look at the high mass MDF for massive galaxies at different redshifts. Lethal Chevalier et al. Measure the MZF for individual quiescent galaxies at different redshifts and find that there's an evolution, the redshift evolution for the iron MZR. But they didn't find any redshift evolution for the magnesium MZR. But whether this redshift evolution can really apply to galaxies at higher redshift is still largely unknown. Mainly because there are just very few metallicity measurements for these high Z quiescent galaxies. And if we really want to know better about the redshift evolution for the stellar MZR Z greater than 1, it is actually very important to keep adding the data points on these two plots. But it's not an easy thing to do, because at Z greater than 1, the stellar continuum of these high Z quiescent galaxies are extremely faint. So it's very, very hard to constrain the metallicity well. But luckily, now we have two candidates. So Jacobs et al. Discovered two high Z gravitational lens quiescent galaxies at Z greater than 1 using an convolutional neural network search from the dark energy survey and the dark energy camera lexi survey. The Rosetta Stones at Z of 1 and the right eyebrow at Z of 1.4. These two lens objects are perfect for stellar metallicity measurements because they are way brighter than other quiescent galaxies at similar redshift. So this year, we spent 11 hours on Rosetta Stones with Elris and Mossfire, and another 3 hours on red eyebrow with Mossfire, so that we can obtain the red string optical spectrum to measure the magnesium abundance and the iron abundances for these two galaxies. And in the right panel, I show the observed spectrums in black and the best fit models in red. For the best fit model, the best fit models are derived from the observer light feeder written by Charlie Conroy. So you can see the model actually works pretty well, and we get very good constraints on the metallicity. I mean, for the iron and magnesium abundances for these two galaxies. Now we can place Rosetta Stones and right eyebrows on the MZ of magnesium and iron. And you can see compared to other previous works, we have a much better constraints on the abundances for these high Z galaxies because the arrow bars are way too small. And also Rosetta Stones put a new constraints on the low mass end of the MZR. And in together with other previous measurements, now we can say as Z greater than 1, the redshift evolution of iron MZR still exists, but we still don't see any evidence for the redshift evolution of magnesium MZR. The difference in the redshift evolution for these two elements can be explained by the stellar nuclear synthesis. Because for magnesium, it is usually produced in the type quark-like supernova of massive stars. And for these massive stars, they have very short lifetime. And then we can say, magnesium is an instantaneous recycled element. But for iron, it is a completely different story. Iron is usually generated in the type 1A supernova explosion, which has a much longer delay time, up to, like a few gigayears. So it is possible that, at higher redshifts, these quiescent galaxies just don't have enough time to have that many type 1A supernova explosions as we have today. And then they just cannot get enriching iron that much compared to galaxies at lower redshifts. And that can cause the redshift evolution we see in this plot. But overall, we have to emphasize that, this conclusion for the high Z galaxies are only based on 6 data points so far. So it's very necessary to have a much larger sample to answer these questions in a systematic way. And we believe in the future, TMT may have the chance to do that, unless someone in Keck Tech, some tech member would like to give us a ton of Keck time and to spend, like a few hundred hours on these very faint quiescent galaxies. And in summary, we measured the integrated metallicity of NGC 147 and compare it with the resolved metallicity derived from the stars. The consistent measurements suggest that we should have a break in the stellar MZR at local universe. Meanwhile, we observe two lens objects, the Rosetta stones and the right eyebrows, to place new constraints on the MZ of iron and magnesium. And for now, we still see, as Z greater than 1, there should be a redshift evolution of iron MZR, but there's no redshift evolution for magnesium MZR. Thank you so much, and I'm happy to answer questions. Sorry, can you say that loud, please?
Any reason you chose magnesium?
Okay, so the question was why we choose magnesium specifically. So if we go back to the spectrum, the reason is because we wanted to limit to a shorter wavelength. We cannot really observe the whole optical spectrum. Otherwise, we'll probably, like not only using mouse fire Y and J, we'll probably use all the mouse fire plus like all the other instruments. And the most important features for these alpha elements is a magnesium B triplet at around 51, 79, 75. So the major reason is because it's easy to observe the magnesium B triplet, while we can observe most of the iron lines at a poorer wavelength. Okay, so the question was, can we sum all the spectrum from the resolved stars of those dwarf galaxies and create a artificial integrated spectrum, and then to recover and see if we can still recover the correct metallicity? Well, that's an option, but for now we are not thinking about doing that, because for these dwarf galaxies, the spectrum are mainly from the RGB stars, so it doesn't really represent the whole stellar population. We can only resolve those very bright RGB stars in the dwarf galaxies. But when we take the integrated spectrum, we'll not only see the light from the RGB stars, but we also see the light from all the main sequence stars, and that actually can account for the majority population of the stars. So that's the reason why we think for now it's safer to get the real integrated spectrum rather than create our own. Okay, so for JWST, this is a really great question. We haven't really thought about it. I think for JWST, the problem is it will take some time to see if because the major problem for now is that we'll need very long exposure time. But JWST is a smaller mirror, so it's hard to say whether the exposure time would reduce a lot. But we think JWST can be more powerful at the spatially resolved spectrum. For instance, for white eyebrows, you see here, if we can observe them on JWST, we'll have a much better seeing. So it's possible to actually study the spatial resolve abundances for these kind of extended length scale.